Here is my Physics Lab 3 black hole and orbits. The purpose of this lab is to demonstrate through coding and physics laws the trajectory of a star around a black hole, as well as the mass of the black hole acting on the star. It's also to determine the velocity of a spaceship around both a planet and moon orbiting the previous star for a particular figure 8 orbit. Here's are the formulas I used. I used the FNet parallel formula, the FNet perpendicular formula, and those two formulas added together give you the net force, which is equal to mv squared over r. I also used the position update formula and the velocity update formula in my code. The result summary. For part 1, the results showed us that by determining the forces acting upon a star in the perpendicular and parallel direction, we could determine the trajectory of the said star and the mass of the black hole acting on the star. We know that the FNet on the star is equal to mv squared over r, as I provided a photo of, and this can help us determine the subcomponents of the force as well. The mass of the black hole we found to be 8.31 times 10 to the 33 kilograms. For part 2, by using Newton's second law and our circular motion laws, we were able to determine a path for the spaceship to travel on the planet and moon without crashing. The initial velocity of the spaceship we found to be 25,000 as a vector, meters per second. Here's our coding and glow script for part 1. The initial conditions showed us that the mass of the star was 2.0 times 10 to the 30th kilograms, and our delta T was 86,400 seconds, which is the amount of seconds in one Earth day. Based on the given velocities and the mass of the star, we can then solve for the change in momentum, dp dt, and set that equal to our FNet on the star. We then solve for the mass of the black hole by setting the gravitational pull by the black hole equal to FNet, since the gravitational force by the black hole is the only force acting on the star. We know dp dt tells us about the change in the velocity of the star. The trajectory of the star is shown below using glow script, and it's unique to my email. The vectors show for cyan that the FNet perpendicular, the orange shows the FNet total, and the purple shows the FNet parallel. Here's our coding and glow script for part 2. The initial conditions were given to us in this case, and we found the mass of the star to still be 2.0 times 10 to the 30th kilograms, and the starter code came with the initial velocities of the spaceship and the moon, with the planet not moving, and all the needed masses, as I've shown in screenshots below. We used our code to calculate all the forces acting on the spaceship, and then calculating a velocity sufficient to make the spaceship not crash. To calculate the forces on the spaceship in circular motion, we use the formula for gravitational force equals negative gmm over r squared. I've also provided a screenshot of the entire code for this section in order to calculate all the forces acting on the spaceship to give us that figure 8 orbit. Although we didn't completely find a figure 8 orbit, we did find an orbit in two separate circles that prevented our spaceship from crashing. What if we were predicting the motion of the entire system? What would be in the computational model? The black hole's gravitational pull has the most influence on the system and that exerts the most significant force due to its size. The planet has the most influence on the moon due to its location and closeness. The star's gravitational influence determines the long-term stability in orbit, and therefore we would also need the mass of each component and the position to determine the overall motion. Finally, what does this lab mean? The net force on the spaceship is determined by the gravitational attraction of the planet and the moon. The net force on the moon is determined by the net force of the planet and the small act of the spaceship as well, although that has much less of an effect. The parallel component of the force determines the speeding up and slowing down of the object, while the parallel component of momentum determines the change in magnitude of the momentum, which is slightly different, but they both deal with the magnitude of the velocity. The perpendicular component only determines the direction of the object for the force, not the magnitude of its velocity, giving the object its curved trajectory that we observed. Finally, the perpendicular component of a momentum determines how fast the object's direction is rotating, / the direction of the momentum, rather than the magnitude of the momentum. Thank you, and that is the end of my lab report.